Chapter 28, Theory Video 7. We are going to discuss the photon energies. So we saw earlier that when electrons change their energy level from one to another, they will either absorb or emit a single photon. So this the energy contained in that photon is going to be exactly equal to the difference in energy levels between the two levels. So that is what we understood as well. Now we know that there are two equations for photon energy, HF and Hc upon lambda. So these two are going to be equal to the difference between the energy levels. So photon energy is equal to delta E. Delta E is taken by E1 minus E2. So as a result, we will get two equations. HF equals E1 minus E2 and Hc upon lambda equals E1 minus E2. Then now to prove this, we can take the earlier example. In hydrogen, electron, if it falls from one energy level, higher up energy level. So here we take the second level to the lowest energy level. Lowest energy level is referred to as the ground state. So it will emit a photon, and the energy difference can be taken, or the photon energy can be taken. Energy difference is equal to photon energy, so you can take it as HF equals delta E, E1 is, negative 0.54 minus 2.18 into 10 to the power 18 joules. So you get 1.64 into 10 to the power minus 18 joules. So using this is the photon energy. Using this you can figure out, because it is HF, it is similar to HF, and because you know H, you can figure out what frequency is. Using the frequency you can figure out the lambda, and then you can figure out which part of the electromagnetic spectrum this belongs to. So that is what here, that is what's given here. Write down a note on this. Photon energies. When an electron changes energy level from one energy level to another, it absorbs or emits a single photon. As a result, the energy of the photon is exactly similar to the difference in energies between the two levels. Photon energy equals delta E, and HF equals E1 minus E2, other one Hc divided by lambda equals E1 minus E2. So I hope you understand. If you have any questions, please raise them, and then do question number 14, 15 and 16 before you move on to the others. Do it now itself, then it would be you would know that you have understood. Then to figure out whether light is waves or particles, the original question that we asked. Now we have discussed in both senses, that is using the photoelectric effect. We discussed that and also remember that this light being sometimes it behaves as waves and sometimes it behaves as particles is not only common to visible light, it is common to all electromagnetic waves, because only the visible light is only a portion of it. We can explain using photoelectric effect. We can explain photons. However, that is the particle nature. However, to explain diffraction, interference and polarization of light, we need the wave model. So, we say that it has a wave particle duality. Wave particle duality. When it, for example, when light is absorbed by a metal surface, or when it goes through the Geiger counter, it behaves like particles. But in other situations, like in diffraction or interference, it behaves like waves. So as a result, we say we give it a name, wave particle duality of light. That is, light interacts with matter like electrons as particles, the photon. So this is the photoelectric effect, and that is the evidence for it. So you need to know, you need to remember what evidence is there for these different situations. Then light propagates through space as wave. So the evidence for this is diffraction and interference of light using slits. Write down, light behaves as waves and also as particles. This is referred to as the wave particle duality of light. Write down, light interacts with matter as a particle. Put a dash and write, the photon interacting with electrons, within brackets the photoelectric effect. Then light propagates, now number 2, light propagates through space as wave. Evidence is diffraction and interference of light. Diffraction and interference of light. Now electron waves. So this is an interesting idea. At the beginning of the last century, Louis de Broglie developed a principle where he imagined that electrons traveling through space as waves. So he suggested that an electron, a particle like electron, can also act as, would have wave-like property. He suggested that its wavelength is related to its momentum of the particle by the equation lambda equals h upon p, where h is the Planck constant as usual, and p is the momentum. So this particular wavelength lambda in this equation, we refer to it as de Broglie wavelength. These waves that we discuss in relation to electrons, we call them matter waves. We know that momentum is the product of mass and velocity. So as a result, because this is a particle, we can say lambda equals h upon mv. The Planck constant is the same constant in E equals hf for the energy of a photon. So as a result, this h is not only applicable to waves, but also it is related to particles as well. So that is a very important distinction that we need to make. Then the wave property of electron was proven experimentally by different scientists who won Nobel Prize for those discoveries. Write down a note. Louis de Broglie, Louis Louis de Broglie discussed that electrons would travel through space as wave and would have wave-like property for electrons. He suggested that the wavelength lambda is related to its momentum by lambda equals h upon p. Lambda, leave a line and write lambda, put a dash and write de Broglie wavelength. Because p momentum, p within brackets momentum equals mv, de Broglie wavelength can be defined as lambda equals h upon mv. I hope that makes sense. Now, this electron diffraction, we can show this property of wave behavior of an electron using a diffraction tube. In an electron diffraction tube, heated filaments would release electrons, and they go through a large potential difference between the negative heater, that is the cathode, and the positive electrode, the anode. Then this beam of electron goes through a sample of polycrystalline graphite. That is, there are many tiny crystals with large number of carbon atoms arranged in a uniform atomic layer. You don't really have to know how they are arranged, but a general idea would be sufficient for you to pass this examination. If you want to know more details, you will be learning about you can learn about these things by reading advanced physics books. So then these electrons that emerge from this graphite film will produce, when it is transmitted to a phosphoscreen, we will be able to see diffraction rings that is quite similar to that of light. That is going to be that is a wave. So this shows that electrons also show wave-like properties. It goes through small circular holes and will produce diffraction rings. So as a result, because diffraction is a property of wave, and because electrons are getting diffracted at this point, as you can see in this diagram, that the electrons are going through this in the form of going through this graphite layer in the form of waves. So they are diffracted by the individual carbon atoms, and the spacing between these carbon atoms. As a result, the carbon acting like a diffraction grating with slits allow the diffraction to take place. Also because the de Broglie wavelength is similar, lambda is similar to the spacing between the atomic layers. So as a result, we can see this diffraction. So then electrons appear as waves. Now if we look at the results, there is another very important discovery that we can make. Now the phosphoscreen will give us flashes of light whenever electron hits this. It not only gives us the proof that we need for the diffraction to prove that it is a wave. So it will develop a diffraction pattern but also these flashes are particles. So we are seeing these individual electrons. So that is a very important discovery that has been made in science using this property. Write down electron diffraction. Electrons wave-like behavior can be observed by using electron diffraction tube, which is made up of a beam of electrons passing through a thin polycrystalline passing through a sample of thin polycrystalline graphite arranged in uniform atomic layers. When electrons pass through these, the individual carbon atoms act as diffraction gratings, and because the de Broglie wavelength lambda of these electrons are similar to the spacing between these atomic layers, diffraction is observed. We can observe these diffraction patterns when these electrons create diffraction rings similar to what's produced by light on a phosphor screen. I hope that makes sense. Now, practical activity. Now we are going to investigate the electron diffraction. So if there is a electron diffraction tube, we can see how a beam of electrons would get diffracted. So there is a electron gun, produced in the usual way. Then we change we can change the energy of electrons and thereby control their speed, and then we can allow it to strike a graphite target. Then we will be able to see the diffraction points on, or diffraction rings on the phosphor screen. Then now we can figure out, we can understand how the wavelength of the electrons would depend on their speed. So what we do is, we can increase the anode cathode voltage and change the diffraction rings. So when we increase the anode cathode voltage, so that results in a faster electron beam, and the diffraction rings would shrink, because the electrons have more kinetic energy. So as a result, when it shrinks, it shows that the wavelength has decreased. So you can use wavelength by measuring the angle at which they are diffracted, lambda equals 2d sine theta. D is the spacing of atomic layers of the graphite, and we can find the speed of the electrode using the voltage. Half mv squared is equal to ev. Using this, we can find out the speed of the electrons. Write down a note before we move on to the other practical activity: investigating electron diffraction. We can observe electron diffraction using an electron diffraction tube as shown below. And please draw this. By changing the voltage between the anode and the cathode, we can change the speed and the energy of the electron beam. When the voltage is higher, electrons have more kinetic energy and they are faster. As a result, the diffraction rings would shrink. The shrinking shows that the wavelength has decreased. Wavelength lambda can be found by lambda equals 2d sine theta. D is the spacing between the atomic layers of graphite, and also the speed can be found using the voltage. Half mv squared equals ev. I hope that makes sense. Now let's look at this worked example. Calculate the de Broglie wavelength of an electron traveling through space at speed of 1 × 10⁷ meters per second. It's simply that you have to use the equations that you have to memorize these equations. So the de Broglie equation is lambda equals h upon mv. The mass of an electron is given. So lambda is equal to h is 6.63 × 10⁻³ divided by mass is 9.11 × 10⁻³ multiplied by velocity is given 1 × 10⁷. So the lambda is 7.3 × 10⁻11 meters. It says that electrons traveling at 10⁷ meters per second have a de Broglie wavelength of order magnitude 10⁻10 meters. So this is comparable to atomic spacing. So the electrons can be diffracted by matter. So that is another fact that you need to understand in relation to the proof of wave-like property of an electron. I hope you understood everything. If you did, answer the question number 17. If you did not, raise more questions. Now moving on to another important part here, people waves. The de Broglie equation applies to all matter, anything that has mass. And also, anything that has mass means even we have a mass. So as a result, golf balls, people, vehicles, anything can have these wave-like properties. So that means everything is made up of energy. This is another explanation for that. Imagine a 65 kilogram person running at a speed of 3 meters per second through an opening of width 0.8 meters. According to de Broglie equation, the wavelength of the person is lambda equals h upon mv. So then that would means he would have a wavelength of 3.4 × 10⁻36 meters. So the wavelength is going to be very small when compared to the size of the gap. As a result, we cannot see the diffraction effect. So as a result, we cannot be, humans cannot be diffracted through these gaps. The de Broglie wavelength is very much smaller than any gap that we can squeeze through. Right? So as a result, we can't actually use this use this phenomena to understand or to explain this diffraction. However, you need to understand that it is actually a theoretically possible explanation. I don't think a note would be required for that. But if you feel that there is anything important in this, you can summarize. Then move on to question number 18. Now we are going on to question probing matter. Now we discussed that anything that has a mass would have de Broglie wavelength. So all moving particles have de Broglie wavelength. So using this diffraction of particles, we can actually deduce the structure of matter. Like now, for example, diffraction of slow moving neutrons, which are known as thermal neutrons, from a nuclear reactor. We can use this to study the arrangements of atoms in metals and other materials. So these neutrons have a wavelength of about 10 to the power minus 10 meters, which is quite similar to the separation between the atoms like we discussed in the earlier worked example. So the separation of the wave separation is 10 to the power 10 meters. That is atomic spacing. That is something that you need to understand as well. 10 to the power minus 10 meters is the atomic spacing. Now we use the diffraction of slow moving electrons to the slow moving neutrons rather to figure out the arrangement of atoms in a metal, and also to identify the structures of complexes such as DNA. And also we use the accelerated electrons, and accelerated electrons, if we accelerate it to the right speed and the right speed, so that their wavelengths going to be equal to the atomic spacing, we can diffract them and observe how they are arranged. Now in this particular situation, an alloy of titanium and nickel is present. Then using this separation, we can figure out how the aluminum and nickel is arranged in a particular order. Then the DNA molecule structure is also observed by using the electron diffraction method. Write down a note. By using electron diffraction, and adjusting the speeds and energies of electrons so that they have wavelengths similar to atomic spacing, within brackets, right, 10 to the power minus 10 meters. We can observe how atoms are arranged in metal structures or in complex molecules. I hope that makes sense. If you have any doubts, ask. So now the electron also has, just like the wave particle duality of the photon of electromagnetic waves. Now we have wave particle duality of electrons, just like the electromagnetic waves. So this is actually, we need to know the evidence that proves these principles. This phenomena is known as the wave particle duality of electrons. So the electrons would interact with matter as a particle. The Newtonian the Newtonian mechanics would provide the evidence for this. Then electrons travel through space as wave. So the diffraction of electrons gives that evidence. Write down. Just like electromagnetic waves, electrons also have a dual nature, which is referred to as the wave particle duality of the electron. An electron can interact with matter as a particle. Put a dash and write evidence in Newtonian mechanics. Then electron travel through space as a wave. Put a dash and write down diffraction of electrons. Now we are going to learn a little bit more about photons before we end the lesson. So the photon has momentum p and energy E. So two key equations can be developed. P equals E upon C and E equals hc upon lambda. Then from this we can get P equals E upon C, P equals hc upon delta lambda C, or h upon lambda. So this equation is identical to the de Broglie equation for momentum of particles and its wavelength. So we can use this equation not only for particles like photon, photons and the wave-like behavior of particles. So this is the de Broglie equation is a very important equation in quantum physics. Write down. A photon has momentum p and energy E. Therefore, two equations for photon are P equals E upon C. Here C is the speed of light. E equals hc upon lambda. H is the Planck constant. Therefore, P equals E upon C, or hc upon lambda C, or h upon lambda. This is identical to de Broglie equation for momentum. Therefore, can be used for particle-like behavior of electromagnetic radiation and wave-like behavior of particles. I hope you understood. That concludes chapter 28. So there were many equations that you have to remember. So let's go through this summary once again to see what equations you need to know. For electromagnetic waves of frequency f and wavelength lambda, each photon would have energy E equals hf and E equals hc upon lambda. H is the Planck constant. Then 1 electron volt is the energy transferred when electron travels through a potential difference of 1 volt, and it has a value of 1.6 × 10⁻⁹ joules. Then a particle of charge E accelerated through a voltage V would have a kinetic energy EV equals half mv squared. Then we discussed the photoelectric effect is a phenomenon that proves a particle-like behavior of electromagnetic radiation. Then Einstein's photoelectric equation we discussed, HF equals phi plus half mv max squared, or Hc lambda equals phi plus half mv max squared. Then phi was the work function of the metal, or simply it is the work function of the metal. Then we discussed about the threshold frequency, that is the minimum frequency of the incident electromagnetic radiation that would release electron from a metal surface. Then threshold wavelength is the longest wavelength. So it is the that longest wavelength that would release electromagnetic that would wavelength of electromagnetic radiation that will release an electron from the metal surface. Then electron diffraction is an example that proves the wave-like behavior of matter. Then the de Broglie wavelength lambda of a particle to its momentum p is given by the de Broglie equation, which you have to remember, lambda equals h upon p. P is the momentum of the particle. Therefore, we can take we can write the equation to be lambda equals h upon mv. Then electromagnetic radiation such as light and matter such as electrons exhibit wave-like wave particle duality. That means they behave like both particles and waves. So in wave particle duality, interaction would be explained in particles, propagation is explained through waves. Photons have no mass, but they have momentum because of the energy. The photon of energy E is given, the momentum P of photon of energy is given by E upon C, P equals E upon C. Line spectra arise for isolated atoms because the electrical forces between atoms is negligible. Then the energy of an electron in an isolated atom is quantized. They exist in specific energy states known as energy levels. Then when an electron loses energy, it loses in the form of a photon, and it would have the same amount of energy between or similar to the energy difference. So there would be an emission line spectrum as a result of that. Absorption line spectra is when a photon of electromagnetic radiation is absorbed by electrons in the isolated atoms. It would the correct amount of energy would be absorbed to go into a high energy level. So unless it meets an electron with a similar amount of energy, it would not happen. Then frequency f and wavelength lambda of emitted or absorbed radiation would be equal to E1 E2 equation. HF equals delta E, that is E1 minus E2, or Hc upon lambda equals E1 upon E2. I hope you understood everything. If you did understand everything, please do all the questions and the exam style questions as well. Then you will be able to understand everything better. If you have any doubts, please ask.